Okay, so I will now be your writer, your scribe, if you want me to put anything on the screen, and we've got everyone here is going to yell at me when I get it wrong. So the royal scribe, yes, yes, very much so. Okay. So John, you'll have to sort of tell us what the problem is and such like, because obviously we don't have any documents. So the floor is yours.
All right, everyone's ready?
Yep.
To be confused? All right.
Extraordinary.
My example was chapter 10.5, but I didn't understand it, so I created my own example.
That's perfect.
Yeah.
So I guess a little background.
That's wonderful. Yeah.
So a little background. I work in a test lab where we do a lot of dynamics and vibration testing. I guess similar for SwiftPack, we do a lot of D5 FBM testing where a lot of the electronic packages, a lot of the packages will get subjected to usually like a sign. Like when I talk about vibration, usually will consist of a sine, shock, and a random vibration test.
Is that swept sign or fixed frequency sign?
Usually a swept sign, yeah. So usually or a lot of times it'll be like a low-level quarter G signature sweep, and a lot of times that's used to, it's kind of usually done before and after tests, and a lot of times that'll tell us if there's any type of problems with the workmanship or if something broke during the actual shock or random vibration environment that was exposed. Or that the
Is this shaker shock?
Shaker shock, yes, sorry. So, yeah, so I guess our lab here, we have a couple of different Ling 335 and 340 electrodynamic shakers. And when I say shakers, they're basically like a big speaker head. So you can imagine, there's a certain spectrum that these packages or these people want, or our customers want their packages exposed to. And so a lot of times, we'll have the specification or profile of what the customer wants, and
just like SRS testing?
SRS or some type of peak G, and that'll be derived, usually from some type of flight test. And especially in the D5 world, a lot of these tests will simulate usually like the launch environments or separation events when this thing is getting launched up into space. So you can imagine, so we have a package, this thing gets mounted on top of this shaker, or we'll call it a speaker. We program it, I guess, I don't know if you want to draw this out or something, but maybe just a simplified drawing of what's going on. So we have a shaker which is going to provide the...
Vertical mount, vertical shaker?
Yeah, we'll say vertical for now. There's different types of shakers, yeah.
Shaker head. Oh, I've just done my separate, it's load spreader the wrong way, there we go. Do you have that kind of configuration? And in concept, we have coils coming down.
Oh, I see. So you get like a head expander or something. Yeah, I guess, yeah. That's.
Yeah. Is this? I mean, are you talking about just wanting to show this kind of thing?
Yeah. So at least as a visual, we have a shaker. The package gets mounted on top of the head there. So yeah, the shaker basically produces an environment, and in this case, it's constrained in the vertical direction, so it'll. Or at least it's not constrained, but it'll, the actual direction of vibration will be vertically. You can also rotate the shaker to provide an environment in the horizontal direction on a slip plate.
Yep. Slip plate, yeah, okay.
There's different types of configurations you can use, or different types of fixtures. But ultimately, so yeah, we have the unit under test mounted on top of the fixture there. And then we'll have a couple of different accelerometers, but for this case we'll just have one accelerometer on top of the package or on top of the on the fixture. And
do you normally mount it on the head expander?
What was that?
Where do you normally mount your accelerometer? On the top of the VUT or right next to it?
It kind of varies. Usually we'll typically mount it as close to the mounting points. But depending on the package, if there's any space constraints, size constraints, or interference issues, it'll either, yeah. So in this case, we're just going to have one accelerometer to, it'll be a simplified version. A lot of times we'll have multiple accels. You'll need at least one accelerometer which will be your control accel. So as how do you say, I don't know, this one accel is basically getting data, and at the same time it's controlling to ensure that the shaker is providing the intended environment. A lot of times you'll have additional accels to monitor different parts of the package. Sometimes you can even put accels on the, on the CCAs or on different parts of the shaker just to make sure that things aren't going to get over-tested. And there's usually also like a test article protector to make sure that that your package isn't going to see something that it shouldn't.
Will that do as a block diagram?
Yeah, so you have the accel, then there's a cable that goes to the signal conditioner. Accelerometers, a lot of times we either use ICP or charge, so yeah, the signal conditioner sometimes it's independent of the black box, but and then the black box, I guess, can be referred to as our vibration control system. And each of these components all have their own calibration that gets cowed in. I think a lot of times we'll send our stuff kit to Stennis to get it cowed, but
you use them. I think you mentioned something.
Yeah, sometimes there's some stuff to us.
sometimes, yeah, the signal conditioning is already built into the black box, but in this case, it's good that we broke it up separately in between the black box and the accel. So, in the black box, it's our vibration control system, so it's controlling the actual environment that the package is seeing, and at the same time, a lot of times they'll often do the data acquisition as well. So, data acquisition is a whole separate issue where you have to consider the whole sample rate. I mean, even like selecting the right accel to make sure that it's not going to get oversaturated or whatnot. But so ultimately, yeah. So we're running a test, we're controlling it. The data acquisition system is acquiring data so that at the end of the test or during the test, you can see real time what the actual package is seeing. Or a lot of times programs or customers will want to post-process this data to, like if you're running a sine sweep or something, it could be the data could be an acceleration versus frequency. Sometimes they may want to see the displacement, so then you can either integrate or take the derivative to get whatever data sets that they want. So that's kind of like the background, I guess. Does anyone have any questions thus far?
It's my little picture at the bottom, plot of something against frequency. Is that about right?
Yeah, yeah. And it's actually, I mean, a perfect example of what we'll usually provide to the customer is, I think was it the control plots that we talked about earlier, where we'll have a control signal right in the middle between the upper and lower control limits, and
Either like that, or
yeah.
sometimes like that.
Yeah.
I just as a matter of interest, do your control lines, are they up and straight, or do you follow the dotted ones where it actually tends to follow the profile slightly more?
Typically, it'll follow the profile. So a lot of times the specs will call out to say the environment has to be within plus or minus 3 dB of the intended spectrum.
Yeah.
So you will have alarm lines which are set more conservatively, let's say at plus or minus 1.5 dB of the actual environment, and then we'll have abort lines which are set plus or minus 3 or 6 dB, and the alarm lines.
Can I just jump in for a second, John?
Sure.
Remember when I was talking about control charts, I said depending on the system, if it's automated, you can have the warning lines, and then you can have the alarms go off and everything shuts down. Typically on these kind of controllers here, as they're doing a sweep through, they do, what did you call it? I think we call it the top line, if you know, exceeds.
Like upper or alarm line or upper control limit?
No, the one beyond that.
Alarm or abort lines?
Abort line, okay. And if the signal hits that, it automatically just shuts the system down. What physical size are your shakers? Are they like about the 2-foot diameter
2 foot.
type guys, or they? Yeah.
It's about
Washing machine size.
Yeah, I guess you can think
Bigger
about
than that,
that. Yeah.
But by the time you've got a lot of energy going into these things, as you can imagine, and so you can't just go click. So it is totally controlled by this thing. For safety, really, isn't it?
Safety for everything from protecting the test equipment and protecting the test article, or customer packages.
Just as a quick side, I had one situation where the customer had the control Excel on the top of a DUT. It was actually they considered this to be the part of the fixture, and the DUT was buried inside the fixture. And they kept on getting a little spike come up, and it was hitting the limit and shutting the system down. And what I found was the top of their, right across here, the top of their fixture was like a cube. Take the lid off, put the components inside, seal it back up again was the fixture. And they had a little resonance right on that frequency. And so this badly designed fixture was causing the sweep to abort all the time.
Yeah, I mean, it seems like a lot of times, the fixture design is definitely something that has to be factored in, just because, especially if you mount the Excel on top of the package, if there's different types of materials, if there's fasteners that are going to go in between, then just the transmissibility of the signal going through all those different components, it's going to...
I forget why they had the Excel on the top, because they had, I forget, it was 2 or 3 Excels on the head as well. But so the control one was put on top of the DUT for some reason in this case.
I mean, a lot of times people will want to put it as far away from the shaker, just because that'll be the highest environment, so...
No, they didn't really have a very good reason.
Okay. And then you can get into like single point control or multi-point control.
Yes, yeah. They were, I think in the end they went on to averaging 2 signals coming in to take out, to compensate for a rock.
And then sometimes if you have, a lot of times there will be some type of resonance frequency, so then a lot of times you can either notch the input spectrum or you can put limiting...
See this core coming down here. I've not drawn it very well there. It's a very simplified schematic, but their main core coming down the middle, they had a resonance in that as well, which was right in the range of that one.
And then a lot of times
actually,
you can
the resonance in that was actually matching the resonance top very closely. Sorry, go on, carry on.
No. Okay. And then a lot of times like you can also put additional Excels to limit or they'll serve as limit channels to ensure that different parts on the package that you're monitoring will not exceed a certain environment, and sometimes there's certain components within a package that just should not see a certain environment. So then, so actually, and then just sorry to go back. A lot of times the shaker shock or shaker vibe, it usually deals with frequencies between 20 to 2,000 hertz. A lot of times, if you want to go anything higher than 2,000, we'll probably usually do it off of a shaker. So we usually do like a MIPS test, which stands for a mechanical impulse pyro shock. And a lot of times, that you can go up to at least the 20,000 hertz range. So, so that's kind of like a test setup in general. But I guess my question came about where a lot of times, we're running these tests, and in a few instances, people will come and ask about the measurement uncertainty involved with the data. So I've kind of seen different sets of calculations on how this can be calculated, but I've never seen anything consistent about it. So kind of, I guess, the simplest would be just to break down each component in series, maybe first with that simple setup of the Excel cable going into the signal conditioner, and then that going into the black box, which could serve as the vibration control system / data acquisition system. And then the other question that I would have is, this is assuming one accelerometer. If I had 50 accelerometers, whether they're in series, in some cases they may be in parallel, what kind of an effect would that have on the resulting measurement uncertainty?
Well, the reason you've probably not really seen it before, this is a horrendously difficult experiment from the uncertainty aspect. Anything to do with vibrations and spectra and such like is difficult. And I think if we just look through the big picture, first of all, there's going to be quite a lot of uncertainty associated with the accelerometer. Do you get the cal charts that show essentially the calibration as a function of frequency?
Yeah, actually I printed out one of our cal sheets, and Yeah, it has a response deviation with respect to. Yeah,
Quite significant, isn't it?
I mean, yeah, it's definitely not linear, and there's a bunch of spikes.
And I'm
but
assuming it's a 1 kilohertz calibration point.
1 kilohertz. Or what do you?
Well, you should see there's the sensitivity or what. I think they do a ratio or something. It hits 1 at 1 kilohertz or something.
Oh, I see. Yeah, I think the reference frequency for this is 100 hertz.
Oh, 100 hertz. Okay. What we have here is frequency and some measure of calibration over here, whether it's sensitivity or ratio. And there's a magic line across, typically, which is the target. And depending on the accelerometer, it may do something like this. Some of them will droop off at this side. This is because it's a physical crystal which we're driving. Which ones do you, and they're not smooth, by the way. Some of these are quite wiggly lines. But you have a target frequency. Yours is 100 hertz, you said?
Yes.
A lot of them are targeted to kilohertz. And basically it's a one-point calibration. At that frequency, that's it. And within your range of 20 to 2 kilohertz, I'm showing that one there, but I don't know what your exact one is.
Mm-hmm.
Here you can be a few dB off, and it's still considered to be a calibrated transducer. So what from your graph, can you tell what this kind of mismatches are at the upper and lower? I'm assuming that the upper and lower are worse than in the middle.
Yeah, no, I mean, it pretty much looks like that. Usually on the ends there, yeah, it definitely deviates. Kind of looking at this plot here that I'm showing for this 1XL, it's showing about a 2.5% difference, which is, actually that's about like a 20%, I think that's 2 dB, so it's about 20-something.
Oh, 2 dB, yeah, it's a factor of almost, well, 3 dB is a factor of 2.
Well, I'm looking at the scale for this particular printout, and it says 1 dB equals 12.2%. So I think, I don't know, actually that's kind of confusing there. But,
yeah, that's about right.
But yeah, I mean, so
50% is 3 dB. That's about right. It's a log scale.
So yeah, it's always interesting to see that, yeah, we have one sensitivity for the entire range, but
right.
That's how it, yeah.
And yet we just ignore that and carry on as if nothing's happened.
Yep.
Imagine that in the world of gauge blocks, micrometers and such like, if you said, this micrometer is only accurate at 1 inch. And if you got a ½ inch, you can have up to 50% error. But that's okay. But that's what we do in the world of accelerometers. Ooh. So that's why when I went back to this page here, where are we? Lost it. Hello. There it is. That's why when I was saying I was going to go through the different topics, the first thing I went to was the accelerometer and said that is going to be one of the major sources of uncertainty. The signal conditioners, what they do for ICP, notice my little comment, hopefully not charge.
No, we use charge as well.
You do not for shock testing, I hope.
No, I guess it depends on the engineer. Some of the old school, I think a lot of people like to use charge.
Charge is good for a sweat sign, which this is that you were showing. If you're doing a pulse, if you're putting a shock pulse in,
yeah.
drop tower type stuff and things like that.
I think, especially if we have if we're using our test article protector, we have to run charge for at least that Excel.
Oh, okay. Because the ICPs tend to have a better temporal time-based response than the charge.
Mm-hmm.
But anyway, the signal conditioner, what the signal conditioner does is it sends in this direction a constant current to charge the electronics inside the accelerometer. And the basic, most of the signal conditioning actually happens with ICPs at least. Most of the signal conditioning happens right down at that point. There's a little microcircuit built inside the accelerometers. And so this tends to be a very robust and noise-insensitive cable. If you're using charge accelerometers, this conditioning now happens inside the red box here. There's this box here. And this cable, at this stage, there is no voltage current sent down. It is now carrying a charge. And this now becomes very, very sensitive to noise pickup, electronic noise pickup. And that's why ICP these days are a preferred accelerometer, because it's the same conditioning, but whether it happens at the accelerometer end or at the other end of the cable, it reduces the electronic pickup or electronic noise pickup on there. So, okay, I jumped in, John took over a little bit there. I don't know if that's, once you get to this point, we're playing with voltages, and typically the uncertainties associated at this stage compared to the associated uncertainty associated with the accelerometer and maybe this first bit of the cable, they're usually very, very small indeed. Come through the power amplifier. Coming back again, this is typically a voltage signal which comes out at this stage, and it tends to be, again, the uncertainty tends to be very, very small compared to the others. Into the power amplifier. And now this is going to have some interaction backs and forwards with this big hunk of metal that's flying around inside here. We try and keep the weight of this thing as small as possible, but it's still big and heavy, I think is the best description I can come up with. So there is some mechanical and electrical matching between the power amplifier and the shaker, and we find that we get structure shaker interactions and all sorts of things like that going on, part of the reason for having a controller to get away with those. And so there can be some lack of form. So if we have a nice sine wave going in here, by the time we've got it onto the structure, the actual signal going up and down here may not be quite as good. It can have some noise to it. It might be losing a little bit of its sine wave type shape. So the key areas to me that I would look at for uncertainty analysis would be here, certainly the accelerometer, because as you just heard, this dB or 2 at each end of the range, and then trying to see if we can come up with anything at that stage. By the way we try to get rid of a lot of this issues is this is a function of frequency. I'm assuming that the black box, if it's putting out, let's say, a 1 hertz, 100 hertz signal, I'm assuming that it very closely filters at 100 hertz before we plot down at this stage. Do you know if that's the case with yours? I think it probably is. The black box has a lot of stuff going on inside. It's a computer. It's a computer system. Do you know, John, if you have close filtering going on?
I know there definitely is some type of filter. I'm not exactly sure how it's set, though. Yeah.
And typically, if you're doing a swept sine here where you put a frequency out and just slowly increase it, because it's a digitally generated inside here, and all right, it goes analog at this stage and comes back and it's digital at this stage, we know exactly how long that time period is. So it can match the filter to be exactly that. And then if you don't need filter work at all, where you get the side lobes and such like going on, basically, if you think of a Fourier analysis, that tends to give you fairly high side lobes. We try and play with windowing to reduce those. But if you're doing a swept sine, the black box typically has a very, very, very high matched filter with huge suppression, because we know exactly the length of the time. We're not trying to do broadband spectrum. And so as a consequence, a lot of this issue to do with nonlinearity, essentially in the whole system, we're getting away from a lot of that because we're only looking at the component weight on the frequency. Does that match as well with the way you're doing things, John?
Yeah, that's a good representation.
Or was that the, oh, is that what we're doing? I didn't say that. Just teasing you. Okay, so do you want to carry on?
No, I think you're going in the right direction. Keep going.
Oh, thanks. So, yeah, it means we're understanding the problem. That's good, isn't it? Yeah. So, essentially, for uncertainty analysis, I would probably ignore this lot. The only time I would bring it into account is if this waveform is grossly away from sine wave. That means that the DUT is seeing energy going in not just at the frequency you're exciting, but also probably harmonics or something like that. And that cumulatively could actually start to damage the DUT, especially if it's an electronic. Is it electronic components you're testing? Seems a little low frequency for those, but
kind of it varies. Yeah, it's just about anything.
Yeah. Because electronic components are very susceptible to high frequencies, or mostly susceptible.
Any issues with phase noise or anything like that? You can't send out signals.
I don't know what this particular black box does, but very often what we do at this stage is not, the algorithms and the SRS calculations are designed to get rid of phase.
Okay.
And depending on whether we look at the, oh gosh, what's that? There are some techniques where we deliberately take again, this is a swept sign, which is a little different. But if we're looking at impulsive or tailored pulsing, that's a better word, tailored pulsing going in, there are techniques where we can actually take the pulse that we want, essentially strip the phase so all the components are in phase, then put that pulse out, and then that gives us the worst possible shock for that phase. And right now it's just slipped my mind. I can still remember the pictures which I'd throw up and such like, and it's just slipped my mind what we call that. But essentially that is, at that stage we say what's the worst possible case we could have for these frequency components, stripped phase, and it's
Is that for
usually
like
done through.
is that the wavelets, or like for shock testing, how you can?
Yeah, it's basically making the wavelets all in phase,
Okay.
because and it takes out any holes in the shock response spectrum. This SRS, this is essentially an SRS that I plotted the shock response spectrum. Here is the Maximax that I plotted there. There are others that are looking at different parts of the profile that can have holes in them, and so you end up not putting any energy in that frequency, and that technique tries to prevent that happening. So yeah, if you get into the world shock, come on the shock course and have fun. Yeah, but this is the course we do on modal analysis and shock.
Okay.
Where we spend a lot of time looking at SRSs and how to tweak signals so that when you put them into the shaker, I mean, it's very easy to generate a theoretical waveform and say, let's put that in the shaker. But then you go say, oh, hang on, I've just put my shaker armature through the roof. Okay, how do I stop it going through the roof? And so all of a sudden, the simple waveform has to have more things done to it.
Breaking the things you're testing, or
Well, it's just an impractical. And so we look at a lot of shaping of pulses and things like that. But this is a swept sign, which is conceptually and structurally for the test equipment much easier. But I bet you do shape pulses. I can almost guarantee with this setup, at the black box level, instead of just putting a sine wave out, you'll put a shaped pulse out sometime.
Mm-hmm.
Do you, John?
Yes. Yeah. So actually, so you were saying that from the conditioner to the black box, you think that
That's pretty clean. Yeah. If you have a separate conditioner, as opposed to using the internal conditioning,
mm-hmm.
if you have ICP accelerometers, it's two different situations. If you have ICP accelerometers, there's a good chance, but not guaranteed, that you have the signal conditioning inside the black box, and then you select ICP as part of your setup.
Yes.
Okay, in that case, you don't have this box here, and the cabling that goes from the black box to the accelerometer is essentially carrying current and voltage, not charge. And it is relatively insensitive to electronic noise. One of the things that we do get is a triboelectric effect, which is the cable, because it's being bounced around at the accelerometer end and is stationary somewhere, wherever you've brought it off the shaker head, the cable is being bent. There is friction, internal friction in the cable, and that can generate a charge, and that is correlated with the signal. And so that's why we tend to like these low noise cables, sort of graphite lubricates and such like, to reduce that. But generally speaking, if you've got ICP conditioning, it is fairly robust, and you don't usually pick up very much of that problem. If you have a charge accelerometer, then what you need is signal conditioning that will give an output voltage which is proportional to the input charge. It's not really a charge amplifier. We're talking about charge amplifiers. They're not charge amplifiers. They don't amplify charge. They give an output voltage which is proportional to input charge. In that case, if this part of the cabling is pretty robust in terms of measurement and certainty, because it's just a voltage which is being carried in a shielded cable. So there is some pickup, but it's tiny typically compared to the signal size. This cable here, though, now is carrying a charge. We're trying to sense the charge generated off the transducer going into the conditioner. Mm-hmm. And so calibration will change with length as opposed to the ICPs when it's a voltage current. I've had like a 2-foot cable and gone out to, I forget it was 200 or 400 feet, and I could see no discernible change in calibration. whereas a charge length here does make an issue, slight issue. Also, it's very, very susceptible to pickup of electronic noise and that triboelectric effect. James is nodding as if he's either agreeing with me terribly or going to sleep. I'm not sure which.
Imitating the bobblehead.
So from a cable
that help, John?
standpoint, yeah. So from a cable standpoint, do we have to factor in any type of? Do we have to factor in anything if it's if it's really susceptible to noise?
If you're using ICP, there's so much more error associated with the calibration and just the general noise associated with the physical test than ever you'll pick up on a cable. If you get a problem, you'll get it so loud and clear that you'll have to stop and check your connectors and such like.
Yeah.
But if they're working correctly, and that is a big issue, by the way, if you've done vibration testing. However, while you connect cables together, with all the vibration going on, they often will just move a little bit or lose electronic contact. So that is an issue. But that's something you check for as part of the setup, routine setup anyway.
So to frame the question, is it, so if I'm going to take the, or if I'm trying to find the measurement uncertainty for this system, is it, would it be just more concerned with like the one Excel that's going to be providing the data?
That's going to be the main source. That's going to be the main source because of the calibration curve.
Yes, okay.
And I have never yet seen a system that actually has multi-point calibration going into it. It just has a single value. What is desensitivity? 91.6 millivolts per G. Done. But there's no reason why they couldn't, but nobody does. Or I haven't come across it. And I doubt that your system does.
Yeah.
So that will be the main source of uncertainty right there. Yes.
So if I had
Now,
20. Oh, sorry. I can kind of hear myself in the background, but if I had 20 accelerometers mounted onto this fixture, do I have to factor in all 20 of these Excels into like just
it's
doing
going
RSS?
to depend what the black box does. If it takes all 20 and averages the signal somehow, and then uses that average signal, at that stage you will be using a 1 over square root 20 improvement in the accuracy. Oh my gosh, I've just broken every rule this little week. But the uncertainty will go down by a factor of 1 over root 20, the number of transducers, if it averages the measurements and uses the average measurement. However, if all of the accelerometers have this curve for their calibration, they will all be down here, and it's a systematic uncertainty that you can't get away from by averaging. This only affects the randoms. So you can have 1,000 accelerometers, and if they're all underperforming at 20 hertz, your answer will be down, including average. That's why we need to build in the systematic type Bs to include that piece there. So basically, you've got the type A squared plus type B squared square rooted, the classic combination we've been looking at. This here is a type B. It's systematic. Every time you go to 20 hertz with every accelerometer, I know they're all different, but let's assume they're the same for now. Every time you go there, you will get that same wrong sensitivity. And in this case, you'll underreport the acceleration, and that affects this part here, the type B. Bringing in multiple accelerometers, you can reduce this term, but even if you got the type A part down to 0 by having lots and 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 lots of accelerometers, you can't get rid of the type B, and that's coming from the calibration certificate. Does that help? Any comments? Does this make sense? Hopefully, what I'm trying to do this here is I'm pretending this is like a mini consulting exercise, so you can see how I'm thinking through the problem and the kinds of questions to ping John with, his feedback, how does it fit into uncertainty. So if you come across a new transducer, they suddenly say, hey, go do this. Here's the standard. Okay, well, you know the standard still needs interpreting, doesn't it? Wouldn't it be nice if it told you, take a red wire and plug it into the green button hole? You know, it doesn't do that, does it? So you need to think about this. Okay, how are we doing, John?
I'm still trying to figure out,
It's tough, isn't it?
just still trying to make sense of it all, yeah.
The other issue that we have, which you are addressing partly already, is that if this platform, instead of going up and down, also has some rocking to it, so it's got some rotation to it. Not if, it does. We try to prevent that as much as possible by having the center of gravity of the fixture and the DUT to be in line with the axis here. So we're pushing, but if we're off axis a little bit, which we will be, we'll get a slight, instead of the platform going straight up, it will go up with a bit of rocking. Now this is a full three-dimensional thing, you're seeing it in 2 dimensions here. And that's typically why we have at least 3 accelerometers set around. And the idea there usually is that we average the accelerometers to try and get the translational components, because if we average, we end up mathematically subtracting out the rotation component.
So if you do if you do a multi-point control, how are you still able to do transfer functions?
Sure. Yeah. Now whether you do it as 3 separate transfer functions and then work in the frequency domain, or you do time averaging, as in kind of short, you can't do it with these, but essentially short the 3 cables, like you do with thermocouples. You know, if you've got multiple thermocouples, you can literally wire them together, can't you? You can't actually do that with accelerometers, but in signal conditioning, you're essentially shorting them together and averaging time, getting the average time. So you can do it in time domain, or you can do it in frequency domain. As soon as you say transfer function, that means frequency domain. And so if you've got, say, 3 accelerometers out there, you could look at 3 transfer functions and try and use those in the frequency domain, or you could average the 3 signals in the time domain and then calculate a single transfer function. And that would be the best estimate of the translation without rotation. Depends whether you need to look at the rotation. If you want to monitor the rotation, then you need to look at each one separately, because the difference between the accelerometers gives us the rotation, the average gives us the translation. So again, it depends what the spec's asking for or what you've been asked targeted to do. So how would we set up an experiment for this then, to try and work out the uncertainty? Any ideas? First thing I'd do is to go to the accelerometer, as you saw, and look at its cal sheets.
If you're saying it's a single point test on that.
So okay, let's go with the single point test then, yeah.
Okay.
So one of the experiments I'm going to have to do is to put at least 2, let's just say 2 accelerometers on there, so that I can find out how much rotation there is. And the reason for that is I need to find out how much is translation of the device under test. Imagine I have that's my shaker head, and my device under test is right in the middle. Can you see this, John, on the camera?
Yes, I see it.
And if I had my accelerometer way over here, now in practice you want it close. It's still off a little bit, so I'm exaggerating it by putting it right over here. We're hoping it'll do this, go up parallel. In practice it goes up with some rotation. So if my accelerometer's on this side, it's under-reporting the amplitude. The controller will increase the input until this sees the required spec, and I'm over-exciting my device under test. If I had my accelerometer on the other side, in that case, the accelerometer is over-reporting the average. The controller will shut down the acceleration a little bit, and I'd be under-testing the device under test. And so if we're going to do for a single accelerometer output, we need to perhaps do an experiment where we run 2 accelerometers and we look at the difference between them to try and assess what the rotation is. It'd be nice to put them on either side of the platform maybe. I'm assuming that the platform is rigid, and typically the manufacturers, going up to 2 kilohertz with these big guys, there's not very much plate resonance to mess us up. There can be some. I think you mentioned about resonances like that. But we can almost assume rigid body, and so we can get an estimate of that. At that stage, we can say, okay, in that frequency range for that particular device under test, blah, 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 we know we've got so much rotation going on, and so depending on whether the accelerometer is on that side or this side, because we can't get in the middle, then that angle, that distance, we're going to be under-reporting by 1%, 2%, whatever it happens to be. So that's an experiment we could set up to try and check the quality of the translation. Coupled with the accelerometer calibration here, those two will give us an indication of how good the signal at this stage is compared to the required translation of the platform. My only other concern then would be harmonics, because it's all locked into constant frequency, and so nonlinear harmonics. I'd just essentially look at the spectrum and say, if my spectrum of my signal here is a nice clean something like that, I'd say, okay, harmonics is not an issue. If I had something that looks like this, I'd say, well, that's probably okay. But if my spectrum looked like this, I'd say, oh, I have some serious issues with harmonics. Nonlinearity in this lower part is an issue. And in practice, if I got that, I wouldn't use it to take data. I'd go back and find out what's going wrong. So that's more of a quality control rather than the measurement uncertainty. And so then the measurement uncertainty comes down to the rotation of the head and calibration of the. Those are my two key points that I would be concerned about. Do you have any other bits you'd look at, John, or is that does that help? Is that kind of
What about the measuring device?
the accelerometer?
No, what's measuring or monitoring the signal from the accelerometer?
It is the accelerometer is the device.
It is the device.
Yes. Yeah.
What reads that?
It's a voltage signal, which, depending on where the condition is, it goes into this black box here, which typically has about 12 bits analog to digital conversion. And the manufacturers of these black boxes go to extremes to make sure that the uncertainty associated with the black box is tiny compared to any signal coming in. That's why I said I wouldn't be worried at that stage. As an example, I've just got to jump onto an example. With vibration testing, if you test a very, very resonant structure, like a bell, for example, and you look at its frequency response characteristics, they'll have a very sharp resonance because it's very little damping, it's bell-like. There'll also be some very, very sharp anti-resonances, we call them. There may be saddle points depending on what we're measuring. And so this is frequency against some measure, maybe a transfer function, maybe acceleration, some measure of level of vibration. With the analyzers that we use, we have to be very careful not to overload, and so the input to the analog to digital converter has to ensure it'll take those peaks. A to D converters notoriously go awful if you overload them. Actually, it's not the A to D converter that can handle it, just it's a threshold and gives you a square wave out. But the algorithms that we run in signal processing do not like truncated data. It's a bit like trying to put a square wave out, and you can't do that. It's all those kind of, it's all related with that. So we set that to the maximum. In the days of 8-bit A to D converters, which was kind of early 80s technology, kind of around about when the first A to D converters came out, 8-bit didn't last long, soon to 10-bit though. 8-bit, we would be lucky if the dynamic range was sufficient that we could get kind of down about here, maybe include those. And the consequence was the signal would come down and then it would look like this, and then it would go back up again. When we got to about 10-bit A to D converters and we thought that the world was wonderful, at that stage we'd get down with the dynamic range and the signal would come down and we'd lose the anti-resonance. Sometimes, yeah, it depends, but essentially we'd lose the real low points. These days, most A to D converters in quality equipment are at least 12 bits, and at that stage the dynamic range is such that we get the whole signal. And if we run the resolution through for a 12-bit A to D converter, essentially if that's causing the problem, then there's something else going wrong with the test. So that's a good question, Dave. And certainly 10 or 15 years ago, I would have been saying, okay, and what A to D converter do you do and such like. But in modern instrumentation, and particularly the controllers that are used for this kind of thing, they tend to be fairly high-end as in quality. And I'm assuming that this is a fairly, who's the manufacturer? Do you remember for the black box?
I
the
guess
system?
there's different spectrodynamics, data physics, crystal.
Oh, you just mentioned one name I don't like, but we'll assume that spectral dynamics is good.
Are you talking
I have a bias, I
data
have a
physics?
bias
Or?
against data physics.
Yeah, but I've heard some horror stories. So
Yeah. One of the earlier analyzers had the wrong algorithm for the Fourier transform in it. So the graphs looked okay until you started to try and use them for anything serious, and you were getting the wrong answers.
actually, yeah, when you go to Eagle Picture, talk to them about data physics.
Oh, great! I will. Have they got data physics?
Or they had, or
Yeah, and there was a huge amount of crosstalk between channels compared to what we want, because crosstalk is correlated and it's really difficult. So it messes up analysis a lot. John, does that kind of help with what we've done? Because the guys here are kind of find it interesting to sort of hear the talk through an issue. We haven't solved anything, but give some ideas. Does that give some ideas?
yeah, no, definitely it's good ideas.
Okay. The plan for the rest of the day is really quite simple. We're going to take about a 15-minute break now. After the 15-minute break, which will put us around about 10:40-ish, we're going to start the final exam. The final exam typically takes 2 to 3 hours. Yes, it really does.